For this lesson, we're going to continue with our look at factoring, and today's lesson on factoring is going to be looking at special patterns that occur. So certain combinations of the trinomial that you're trying to factor, it's not even necessarily a trinomial, of the quadratic that you're trying to factor. So let's visualize, let's see that with algebra tiles. So in this case, we've got an x squared plus 6x plus 9. I will assemble my 9. So I did my x squared first, and then I'll do my 9. Now I've got a number of options for 9. I could do 9 tiles spread out lengthwise, but something that I've been trying to do whenever possible is to make things more square and less long and rectangular. So rather than that shape, I want shapes that are more like this. They're not necessarily going to be perfect squares, but I want the edges to be as close to equal as possible. And so in this case, because I've got 9 there, well, actually I can make a square. And now how do I fit positive 6x into this? And it turns out that actually fits quite nicely. This is one, it's only one, but it's one of the reasons why I encourage you to go for that more squarish shape, because it causes situations like this to work out very quickly and easily. And so what do I have here? I have an x across the top and then plus 3, and I have an x along the side and a plus 3. So this is equal to, if you just wrote this out blindly, you would say, well, that's x plus 3 times x plus 3. But x plus 3 times x plus 3 is actually the same as x plus 3 all squared, because these two factors are the same, so it's just that factor squared. Okay, well, that worked out fine, and that has something to do with this idea of special patterns, but we maybe have to go a little bit deeper into it. So let's do the same thing algebraically, and we'll use the idea of SPI. So what is our sum in this case? Our sum is the middle value, so our sum is equal to 6. Our product is equal to 1 times 9. Of course, you don't need to write that if you can go straight to 9. So I need two numbers that multiply to 9 and add to 6. And those numbers are pretty obviously 3 and 3. So 3 times 3 is 9. Positive 3 times positive 3 is 9. Positive 3 plus positive 3 is 6. So this becomes x squared plus 6x plus 9 can be broken into x squared plus 6x gets broken into 3x plus 3x plus 9. I do factoring by grouping. These two first terms have an x in common, and then I have an x plus 3 left over when I divide by x. I bring down my plus sign. The numbers 3 and 9 have a 3 in common. There's nothing to do with the variables because there's only a 1 here. There's no x's. And so 3x divided by 3 is x. Positive 9 divided by positive 3 is positive 3. And you can see we have the same factor here in the brackets. So I'm going to factor that out, x plus 3. And then what's left behind is an x plus 3. And again, x plus 3 all squared. So now that I've done that, I've done it with algebra tiles, I've done it using decomposition, which is the part where I break these into two pieces, and then factoring by grouping. So if you're observing this, maybe you're seeing some sort of pattern, but let's do another one just to reinforce it. This one's quite a bit more difficult, and it's going to take up quite a bit more space. I'm not sure if it's even practical to do it, but let's see if I can fit it on here. So now I've got 4x squared, and again there's 4 of them, so this one I'm actually going to take that opportunity and make a square. And then I've got plus 9, so once again I'll make it more squarish, so that means I'll make a square down here wherever possible. And then, oh sorry, that's only plus 6, I need plus 9. and then I need negative 12x. Well, that's interesting. Does it work to put negatives here? Well, I've got negatives here, but a positive here. So the only way that would work would be if these are negatives as well. Because then I would have a negative 1 times a negative 1 gives me a positive 1. And it turns out that that actually is the correct solution, because on these vertical ones I get 6 of them, and on these horizontal ones I get 6 of them. And when we combine those, I end up with a total of 12 negative x's, which is negative 12x. The sides of this shape, I have an x, negative 1, negative 1, negative 1, an x, negative 1, negative 1, negative 1. And so we end up here with x minus 3 times x minus 3, or x minus 3 all squared. So I'm going to start to point out some things. Well, take a look now. I want you to specifically, the fact that I got a squared here, this has happened twice now. And take a look at, I'm sorry, I actually did that wrong. It's not x minus 3, it's 2x. 2x's minus 3, 2x's minus 3. So squaring this, 2 squared is 4, x squared is x, negative 3 all squared, negative 3 times negative 3 is positive 9. And then we've got this term in the middle. A common mistake that people will make is they take a look at this, they see the squared, so they square the first term, they square the second term, and they completely ignore the middle. You need to remember to expand these things honestly. Okay, what about doing the same thing algebraically? We have a sum of this middle term, that's negative 12. We have a product of the first term times the last term, and that's 4 times 9, that's 36. What are two numbers that multiply to positive 36 and add to negative 12? And so 6 times 6 is equal to positive 36, but I want to add to negative 12, so I actually do negative 6 times negative 6. So those are my two integers. And so this becomes 4x squared, and instead of negative 12x, I'm going to write that separately as negative 6x minus 6x plus 9. Between 4 and negative 6, I have a common factor of 2. Between x squared and x, a common factor of x. Dividing that out, I end up with a 2x minus 3. I bring down that negative sign. Between 6 and 9, there's a common factor of 3, but because of this negative sign, my factor is negative 3. And between x and 1, there's no common factor, or the common factor is 1. So I just leave it. Negative 6x divided by negative 3 is positive 2x. Positive 9 divided by negative 3 is negative 3. These terms, these factors, not terms, these factors are the same, so I factor them out, 2x minus 3, and then what's left behind is a 2x minus 3, and not surprisingly, 2x minus 3 all squared. Now this is just hideous. Of course, I'm not going to do this using algebra tiles. 25x squared, 9, negative 30x. But the thing I want you to notice, again, this idea, we've got special patterns happening here. 25 and 9, what's the significance of those? Significance of those is that 25 is actually 5 squared. 9 is actually 3 squared. And obviously those squareds have been coming up. You probably should suspect that this answer is going to be something all squared. Some binomial all squared. So when we factor these special quadratics, that means they have a special pattern that goes along with them. The one we've been looking at so far is called a perfect square trinomial, and it can have one of two patterns. Basically, it has a positive pattern and a negative pattern. And we looked at one example of each. So if it's in the pattern a squared plus 2ab, so this is the positive pattern, plus b squared, the binomial ends up being a plus b all squared. If you have a perfect square, a squared minus 2ab plus b squared, another perfect square in the end, so this time it's a minus, we end up with the pattern a minus b all squared. You can use algae tiles provided it's not a crazy one like the one I just showed you. I wouldn't want you doing 25x squared using algae tiles. Or you can use decomposition, which we've been calling SPI. Decomposition is where you take that middle term and you split it into two terms. That's the I part. Well, that's decomposition using the sum and product. And that can work, but it can take longer. But if you happen to, once you become familiar with it, if you can pick out these patterns, then you can go straight to the answer. But a word of warning that goes along with that: you can have a perfect square at the beginning and a perfect square at the end, but unless you also have either plus 2ab or minus 2ab, unless that middle term works, it's still not a perfect square trinomial. It has to have all three of those components. So let's take a look at a few examples where we're going to predict our possible pattern here, then we'll check it, and then only then will we answer it. So I don't want these, I'm not going to factor these using SPI. I'm just going to factor them if I can use a pattern. We've done practice on SPI in the past. So I take a look at this. What is my A value here? What is the thing being squared? The thing being squared here is an x that is being squared. And you might wonder why you're writing it this way. Just go with me. Something is being squared here. Something is being squared here. Well, what's being squared here? A 6 is being squared. So the possible pattern would be x plus 6 all squared. The first term plus the second. Why did I know plus? Because I see a plus sign here. Now, to check that, what I want to do is I want to take 2 times the first term times the second term. So there's the first term, there's the second term. Well, what is 2 times x times 6? Well, 2 times 6 is 12, and there's an x left over, but that's what I have here. So this checks out with this. So my answer here is x plus 6 all squared. You don't necessarily have to write this stuff out once you become very good at this and familiar with it. You will get to the point where you can do it in your head, or you don't even have to write out all these steps. But for now, this is what you should be doing some sort of check over in your rough work. You don't have to write this part, you don't have to write this part, but you do need to double check your work. So for this next one, what's my possible pattern? Well, again, I have an x squared and I have a 6 squared. I think I've made it maybe too obvious why this one's not going to work, because my possible pattern here is x plus 6 all squared. But now I need to check 2 times this term, which is x, times this term, which is 6, but that's 12x as we found in the previous. But that does not match. 12x does not match 13x. Oh, that doesn't look good. That looks like another x. Okay, so this does not match this, and so this one we can't factor using a pattern. And finally, a little bit more involved here, and now hopefully you'll see why I was suggesting that you put these brackets. What am I squaring here? I'm squaring 2x all squared. 2x times 2x is 4x squared. What am I squaring here? 5. So my possible pattern is 2x plus 5 all squared. That's my possible pattern. So I take 2 times what? I bring down a 2x, I bring down a 5, and what is that equal to? Do the numbers first. 2 times 2, that's 4, times 5 is 20, and then there's an x. 20x here, negative 20x here. Oh, made a mistake. I wish I could say I did that on purpose, but I actually just wasn't paying close enough attention. So that is supposed to be the pattern 2x minus 5. That would change this to a minus 5. That would change this to a minus 20. And now things work. So the answer to this one is 2x minus 5 all squared. Okay, so you do need to check that middle term. Okay, let's take a look into our second pattern now. 4x squared minus 9. So you probably have at least a rough idea of how this is going to go. But obviously this is quite different, if for no other reason, than this has two terms. We still have some perfect squares going on here, but I only have two terms. And the last term, the number, is negative this time. Before, the number was positive. So let's see when I put my values in here, or my tiles in here, what kind of pattern emerges. Okay, so that being the case, what can I fit in here? Now this -1 means that these tiles are going to have to be a different color than these tiles. So I'll put pluses here. And I will put negatives on the vertical. And just like I was doing with my algebra before, I do need to double check what I'm doing here. And so I've got, well, let's fill some of this in. I have an x here and an x here, an x here and an x here. X times x squared, all the x squareds work just fine. I have a -1 here and a 1 here. Well, -1 times +1 is equal to -1. -1, 1, 1, and -1. So that all seems to work. I have that square shape, but this isn't called a perfect square. This is something else. What is the top? That is 2x minus 3. And what is the side? That's 2x plus 3. So it's a very similar pattern to that perfect square we just finished looking at. The first term is a perfect square. The actual value of the second term is a perfect square, which is 9. But because of this minus sign here, we've got one of them with a minus and one of them with a plus. Now, what would it look like if we did that using algebra? So, and this is something that throws people off right away. As soon as I ask for the sum, sometimes students will look at me and they won't understand what to do. So let me just bring this down. 4x squared minus 9 is 4x squared minus 9. And how many x's do I have here? What goes in the middle? Normally it's an x squared and an x and a minus 9. So how many x's do I have here? I have 0 x's. And 0 times x is 0, and that's why we don't normally write this. But it is there. So my sum is actually 0, and my product is 4 times -9, which is equal to -36. Well, let's think about numbers that multiply to positive 36, but we want them to add to 0. And this time I'm actually going to do this the way I did it when I first introduced this idea. So 1 times 36, 2 times 18, 3 times 12, 4 times 9, 6 times 6, 9 times 4. Okay, I've gone around. I'm duplicating things here. The product is not positive 36. The product is negative 36. Now, when we've done this before, we've asked which one should be bigger, the positive or the negative, but they add to 0. That means that neither the positive nor the negative should be bigger. It means they should be the same. Well, the only way to do that is this one. I'll make one negative, I'll make one positive, they'll add up to 0. So my numbers are -6 and +6. So 0x, so just take a look at this after I write it out, -6x plus 6x minus 9. Would you agree, and obviously you can't answer me here, would you agree that -6x plus 6x is 0x? And normally we wouldn't show the 0x. So long as you find all of that consistent, making sense, we can proceed. For the 2 and the 4 and the 6, I have a common factor of 2. X squared and x, I take out a common factor of x. What's left behind is going to be a 2x minus 3. I bring down the plus sign. Between 6 and 9, common factor is 3. And what's left behind is 2x minus 3. Now I have a common factor of 2x minus 3. And what's left behind is a 2x plus 3. And this is the same pattern we saw when we did it with algebra tiles. I think I'm going to skip past this next one. It's just more of the same. So now we're looking at what are known as difference of squares. A difference of squares is when we have a pattern. We have a perfect square at the front, we have a perfect square at the end, and they're separated by a subtraction. The pattern is a plus b times a minus b, or a minus b times a plus b. It doesn't actually matter the order. Now the nice thing about this is because the middle term is 0, there's no check you need to do. So long as you've been careful and you actually do have perfect squares at the beginning and end, you should be fine. So this one is k squared. Actually, I'm just going to go ahead and write it. I'm going to say this is equal to k all squared minus, and then 121 is the same as 11 all squared. And so what is the pattern? I've got a perfect square minus a perfect square. So I take a plus b, that's k plus 11, times a minus b, that's k minus 11. In this one, I have 81, which is 9 squared, and I have m squared, so that's m. So this one is 9m squared. And I have 144, which is 12 squared, and they're subtracted. And so that is equal to 9m plus 12, 9m minus 12. And if you can see it, you can go straight to this as your answer. Okay, for these ones, we're just going to look for the overall special pattern. Some of them will occur quite readily. Others, you might have to do a check. So I'm looking over here at B. The other thing is, and I haven't mentioned it up until now, but it's important, I've mentioned it in previous lessons, the first thing you always want to look for is common factors if they exist. That's a pretty big hint for one or two of these examples. So let's do that right from the beginning. First of all, are there any common factors between the number 25 and 144? No, there are not. So we don't have to worry, and there's no common factors between variables here. So no common factors in this one. This looks like a difference of squares, and so 25d squared comes from a 5d, and 144 comes from a 12. So I'm going to say 5d plus 12, 5d minus 12. Okay, if you wanted to do an extra step in that one, we could have actually said that's 5d all squared minus 12 all squared. So then it's this first one plus the second one, the first one minus the second one. Now let's move over to part B. Any common factors between the numbers 16, 24, and 9? No. X squared, xy, and y squared? No. Now this one's a little bit weird because of the presence of the y and the y squared. When you run into something like this, focus on, what if I gave you this, 16x squared plus 24x plus 9? You'd be able to handle that one, I think, just fine. So what do we have here? And it's going to work out the same. 16x squared is the same as 4x all squared plus 24xy plus 3y all squared. I'm using that same trick where I'm writing these things. So now, if this is a perfect square, then what should this be equal to? Just to remind you, this middle term is 2ab, which is 2 times, what would the a term be? That's 4x, And what would the b term be? That's 3y. 2 times 4 is 8, times 3 is 24. X times y is just xy. And that is the same as that. So we're good. It is a perfect square. And so we can write this as 4x. It's a positive perfect square pattern. So it's 4x plus 3y all squared. Now, how about this one? Between the numbers 18, 60, and 50, is there a common factor? And as a matter of fact, there is. I can see they're all even numbers, so it's definitely the number 2. Can I fit a bigger number in there? Well, you can probably eliminate that pretty quickly. What numbers go into 18? 2, and then 9, 2 times 9, which is 2 times 3 times 3. So you know what? I'm just going to go ahead and write that. 2 times 3 times 3. What is 60? 60 is 6 times 10. But 6 is 2 times 3, and 10 is 2 times 5. And then 50 is 5 times 10, but 10 is 5 times 2. So what do these all have in common? The only thing they seem to have in common with each other is the number 2. P squared, P, and Q. There are not P's everywhere, so I can't take anything in there. Q, Q, and Q. I can factor out a Q. 18 divided by 2 is 9. P squared stays as P squared. Q divided by Q is 1. Negative 60 divided by 2 is negative 30. P stays, and Q divided by Q is 1. 50 divided by 2 is 25. Q divided by Q is equal to 1, and so that's what we end up with. And now, 2Q, I've got a potential perfect square pattern here. And this one is going to be the one with the negative sign, because I've got a negative here. So if this is a perfect square, what is it that I'm squaring here? That is 3p all squared. And what is this? That is 5 all squared. And so if my pattern is correct, then my answer is going to be the 2q in front, and then this bracket is going to break into, or not break, it's going to factor into 3p, and it's going to be minus 5 all squared. And just do a double check. Even if you do that over here in some rough work, the double check is 2 times the first one, which is, the first value, 3p, times the second one, which is 5. 2 times 3 is 6, times 5 is 30p. And we have a negative 30p, but we have a negative sign here to take care of it. Actually, I should have said minus 5, because I did a minus 5 here. So that would be minus 30p, and that's correct. And for the last one, common factor, well, they're both even, so I can see that 2 goes into both of them. And then this one is 2 times 49, which is 2 times 7 times 7. This one is 2 times 16, doesn't have anything to do with 7s, so it's just going to be 2. A and B are separate, so can't do anything there. So this becomes 49a squared minus 16b squared. And that's equal to 2. And now the perfect squares I have here, 49a squared comes from 7a. So this becomes 7a. 16b squared comes from 4b. So this is 7a plus 4b, 7a minus 4b. And I feel like I rushed that a little bit, so I'm just going to back that out a little bit. And I'm going to take my time here. And let's look at, just to write it out, what is 49a all squared comes from 7a. 49a squared comes from 7a all squared. 16b squared comes from 4b all squared, and I'm subtracting those. So the 2 in front is because of this common factor. And then inside, I'm going to put a square bracket now to represent this whole thing. That can be broken down into 7a plus 4b, 7a minus 4b. but you can see all we have is multiplication here. Multiplication, multiplication. So I'm just going to write this as 2 times 7a plus 4b, 7a minus 4b. Okay, and that's it. Different patterns. One of them is called a perfect square. The other one is called a difference of squares.